Hello? Oh, well, that works. Okay. I don't know what I broke on. I must have broke something. Um, but I'll leave it for now. So I guess what I'm curious about and I'm about to go check is, did I really stream all yesterday and I didn't check volume, and because of that I now have a stream with absolutely no volume? Alright, cool. No, we're good. I definitely have volume yesterday, so whatever's going on right now is just a function of some kind of lag. Anyway, glad I fixed that, or glad I checked that. It would suck to stream for an hour and a half and not be able to go and back and listen to some of these. I also recognize that, I mean, part of what makes these recordings really useful is also just that, for prosperity's sake, in terms of my own thinking process, I can go and reflect on how I originally thought about some of these problems and now how that thought process has developed as I continue to move forward through these examples. Yeah, welcome back to Bayesian Cognitive Modeling, a practical course. Sorry for the technical difficulties right in the beginning. Today we're gonna keep going like we were. Have been for the last couple of days. We finished chapter 5 yesterday. We're going to start with latent mixture models today. And essentially, latent mixture models are, what's the best way? A means for identifying properties that might vary across groups, and and letting the data identify those clusters. Yeah, so we have some groups, right? I think that's like the intuition behind it. Is like we have some groups, but we didn't necessarily observe any data that would help us classify those groups from one to another. However, we can use the data to infer some sort of unobserved latent grouping between the observations. So that's what we're going to do here in chapter 6 with these examples. I'm really excited. These examples are much more applied. Not that the prior examples weren't applied. I mean, it is called a practical book. But now we're going to, I think even starting here, assessment of malingering, we're going to use real data sets from papers and stuff. So we're going to be able to see how this stuff gets used in the wild, in addition to seeing some of the toy examples that we've seen up to this point. So this is exciting. So we're just going to get started then. Setting width. Page 77. Okay. Great. We're going to start with exam scores. So we've got 15 folks, and they're going to take an exam, and it's 40 questions. And here are the amount of questions that they got correctly for each of the 15 people. And it looks like some people are really bad, just guessing almost. And some people had some level of knowledge. And so we want to know if that's the case. Can we identify the guessers and the non-guessers? Are there different rates of success or probabilities of answering the question correctly from the guessers and the non-guessers. So we want to know there's this latent group of people who are knowledgeable and not knowledgeable, and we want to identify that. So that's what we're going to do. We're going to infer which group a person belongs to based on the rate of successes from all the folks. So let me pull up the data. Oh, JText. Yeah, JAG specific code, JAG's R script. This is going to be a little different in terms of approach relative to the text, what's written in the textbook. Use my handy dandy new shortcut, Command F7. So I can put my JAG's text over here. And lastly, we're just going to set the working directory here. So now we don't have to worry about that. And we'll bring that. Good. And then we'll check to see if this code works. And the code works. And it gives us those ugly plots once again. And we're also just going to print the samples. Cool. Looks like we're getting fee, and then we're getting a value demonstrating if they were in one group or another group for each of the 15 subjects. And it looks like those, just like the data said, 1 through 5, are in the 0 group, which is the non-knowledgeable. 6 through 15 are the knowledgeable group. And let's get under the hood into the code then, and we'll talk through some of this. But first, let's just look at the JAG. Okay. So here, this box represents that these are all the components of this graphical model belong to a given person, right? So we have n is equivalent to the number of cases that we have here. So in this case, it's going to be 15. K sub I is going to be equal to the observed success rate that we have for each person. So that's going to be the scores here. So score I sub K sub I for subject 1 is 21, right? And then we want to know the success rate, which is determined. So the success rate being the probability of answering a question correctly, which is determined by Z sub I for a given person, which is a unobserved indicator. So this is the mixture model, the latent mixture portion, where we want to know if this is a 0 or 1 for a given person, and we have information about the success rates, and we believe that these success rates are different for the two people. So in this case, we have here where we think that these are the guessers. So you see it would be 50%. So a success rate of 50% is guessing here. And we're just saying that a priori, where if someone was guessing, then give them this guessing as their success rate. However, if the success rate, if Z is equal to 1, then the success rate is this value, which is the same for each subject, which I think we'll talk about later, but is probably not the best. We probably want some distribution of values for phi here beyond just everyone gets the same phi. Yeah. It'd be nice if everyone had their own phi rather than this being a fixed effect sort of thing. And so this is distributed Bernoulli 50. So 50-50, we're not sure if it's 1 or 0, right? And then this is a uniform distribution from 0.5 to 1. And we choose 0.5 here because we don't want these two distributions to overlay, right? So this starts at 0.5, so this has to be 0.5 or above. So something above chance makes you so that you are knowledgeable. And then K is binomial, so it's modeling success rates for 20 folks. 15 folks, sorry. Let's take a look at the code then for the JAGS model, because I'm curious to see how they went about coding this up. So we have a for loop here for each person. We have Z, which is distributed as a Bernoulli 0.5. And then the first group is guesses. The second group is the rate of success. It's uniform. And we have a Bernoulli distribution for the success rate where for a given person, theta, we're using this equals function again, which is equivalent to saying, if Z sub I is this, then if 0, then do 8 times phi. So if Z sub I is 0, then multiply it by psi. However, if Z is equal to 1, so we think it's part of the knowledgeable group, multiply it by phi. And so K then is the successes, which is binomial distribution. Cool. And then in the R script, we just get the scores, the length of the number of people, number of questions, the data, and then we have to initialize. And what is this? Z? What is Z here? Right, we have to initialize values for each person for Z, because each person needs an indicator. So we set some initial value for that person, which is random 0 or 1, but ultimately it's going to, that's just for our sampler. And we care about phi and Z. Then we sample here, and then this gives us our samples. Cool. I'm not too interested in the plot, to be honest. The plot's not that informative. I guess this little plot is sort of informative. Something I would like to see is like it's like a discrete count of Z's for 0 and 1. That would probably be nice. But ultimately, I think we have all the answers. I think we have all the knowledge we need in order to answer some of these questions. So draw some conclusions about the problem from the posterior distribution. Who belongs to what group? How confident are you? All right. So as we can see here in the posterior distribution, we can move that. And let's print it again. Here's the posterior distribution. 0, 1. So there's 2 people where we're pretty sure, but there's a little uncertainty. But it seems like the first 5 people were identified as being, like I said before, the guessers, and 6 through 15 identified as the knowledgeable, corresponding to what we thought. And for the knowledgeable group, people on average tended to have a success rate of 86%, which is pretty high. Yeah. Right, so I mean, they're getting it right way more than the people who are guessing, and it's pretty clear. And that's cool. So we didn't say anything about this, right? So we inferred this z value for each of the individuals just from the data. So that's this is like a latent group that was identified via the inferential technique here, that being latent mixtures. So magic, right? Common theme in statistics. I'm pretty confident in these groups. I mean, we don't see much variability or uncertainty in the estimates. Nice. The initial allocations of people to the two groups in this code is random, and so it will be different every time you run it. Check that it does not affect the results from sampling. All right. So just run it again. Okay, we ran it again. First 5, still 0. Let's run it again. First 5, still 0. Run it again. First 5, still 0. So you see, I mean, we're running it every time, and we're still getting the estimates here. The 6 and 7 are like, I think 31 must be some cusp of sorts. What would be 30? Even lower, but even so. So you can see that setting an initial starting value for z isn't affecting our results. Include an extra person in the exam with a score of 28 out of 40. What does their posterior for z tell you? Now add an extra 4 people. Alright, so let's take a pick. We got someone who scored 28 now. It doesn't know where to put them. It's like it could be either or. Not sure. Now add an extra 4 people, all with a score 28. So now add 28, 28, 28. Oh, I see. More evidence of 28 tells us if it's a good score or not. So we're getting a couple more people, but notice how the probability of being a part of the knowledgeable group increased when we added additional samples of 28 as a score. So before, 28 looked like the lowest score it was like the lowest score threshold, right? Notice how this also changes the results for 6 and 7, where 6 and 7 before were the lowest score before the threshold. So there was some surrounding uncertainty, even a little bit here for 7, in terms of whether it was part of the knowledgeable group, because there was some cutoff between the values. But now the cutoff is 28 because we have more values demonstrating that potential, or the 28 as a viable outcome, or number of getting correctness, number correct in the problem. What happens if you change the prior on the success rate of the second group to be uniform over the full range, and so allowing for worse guessing performance? All right. Let's change this back. So we have 15 folks. Now we're just going to go in here and we change the prior to allow from 0 to 1. Not much. Not much changes. Phi changes a little bit, but it's so clear the partitioning between the two values that it doesn't seem like the prior impacted the data, or impacted our posterior in this case. Good. Yeah. No real impact here. Alright. What happens if you change the initial expectation that everybody is equally likely to belong to either group, and you have a expectation that people are generally not guessing? So instead of this, it's asking, well, what if I say, generally we believe that a person is not guessing. Still, no change. Look at that. So these priors are really not moving, are not influencing the results. The results seem to maintain themselves under varying priors here. I mean, even here where it might have been possible that an individual, it's like slight, that's random variation, right? It's not. Next problem. So, previous example shows how sampling can model data coming from mixture sources and then infer properties of these latent groups, right? So we were able to identify whether someone was knowledgeable or not, or guessing. And that's the property based on what we observed the scoring on the test. I was just checking the stream. Need to get better at checking the stream. Okay, noted. All right. So one straightforward way we can allow for individual differences in the knowledge group is by extending the model hierarchically. So in this case, it's like if you are aware of mixed effect modeling or multi-level modeling, this would be changing phi. Right? Am I saying, is it phi? Let me make sure. Yeah, changing phi to a random effect rather than a fixed effect. So instead of everyone having the same success rate, the success rates for a given subject are from a distribution, an underlying distribution, which is distributed by mu and lambda. So what that's saying is that we can have individual scores of success for each person. So we can account for variability in the scores across each person, right? Yeah. I don't think that's what it's doing in this case, but I think it's just allowing us to gain insight on the particular success rates for each individual. So, yeah. So in this case, we're just extending the model such that now it's all here. Everyone had the same. Everyone who was knowledgeable had the same value for phi. Now, each person, phi sub I, is so that each person has their own value of phi, and this is going to be distributed by these two parameters, which we don't observe. So we're going to estimate the average and precision for phi. Everything else is the same, essentially. Let me see what it says about. This is in exams 2. Cool. Oh, no, I almost forgot again. We'll do it for this one. So for exams 2, I want to pull up the stand code too. I'm going to pull up the JAGS code first. Parameter selection. Mixtures. Exams 2 JAGS. And then exam 2 JAG. What is over here? And then, so I don't forget this time, I'm going to go get the stands code. So I can at least just take a look, even if I don't run it. Docs. I should really just figure out where the stand code is. Put it somewhere easy to access. But I like the file structure right now. And just a reminder, Stand is just another probabilistic programming language that can sometimes more efficiently solve specific types of problems based on its syntax. And it allows us to solve, right, it just allows us to solve problems. Down the road, I've heard that it allows us to solve problems easier depending on the problem. So it's nice to have exposure to both sets of code. Additionally, I've found just from exposure online that there are a lot of powerful tools that interface with R that allow us to take advantage of the objects that are extracted using Stan. And then moving forward, there are even packages that are built on top of Stan that I wouldn't even have to even code in Stan. I could just run models using those, which then write the Stan code themselves, and that's going to be easier. Once I get an understanding of what's going on under the hood, I'll feel more comfortable taking advantage of those options. So this is sort of the building process for that, getting to that stage. All right, so in this case, all we did then, let's make sure the code works. Like always, I'm just going to add the print samples. Cool, and that's going to work. Nice, and we're also going to get, so we're going to get these data distributions for each of the folks here. That's going to be cool. So we get all that out of the model. I can see why we're not printing after a while now. Let's look at the code then. So I, for each person, our success rate is going to, if it's 0, it's going to be, if z sub I is 0, then multiply it by psi. If z sub I is 1, multiply it by phi for a given I, for a given person. And then k is the success rates, the scores, which is binomial distributed for a theta for a given person, and the total number of folks. Each person belongs to 2 latent groups, so I for a given person is z, and it's random, which we're starting out with a Bernoulli distribution, 0.5. We don't know where you're starting, where you go. The second group allows for individual differences. So for a given person, phi is distributed normally. So this is that hierarchical structure we're adding. It's going to be distributed mu lambda with t 0, 1. I don't know what this means. Find t. Let's see, I'm looking for some, it looks like it's a censoring tool of sorts. All right. Looks like there's some insight here. Also, even though you might be able to use I notation, I think JAGS generally uses T notation instead. JAGS, T notation. JAGS T notation meaning. Transpose. That's not what we're talking. Capital T is something different, I think. Mm. There we go. We have I. Here we go. Truncation is represented in JAGs using T, which has the same syntax as I, but has a different interpretation. So, say X is distributed in dfoo theta T LU, then a priori X is known to lie between this interval and generates the following likelihood, where X given the parameter over the probability given some parameters. So we're looking at this range. So phi distributed mu lambda truncated such that it's bound to be between 0 and 1. And we do so because these values can extend beyond that. However, it doesn't make sense for it to extend beyond that because we're looking at success rates, and we can't have negative success rates, right? Okay. So T is truncation, and it represents an interval similar to that of I in bugs. Cool. Thanks, internet. Okay. Where are we? So here, truncated, so it's a censored distribution. So the first group then we just specified is 50 because it's guessing. And then the second group, we have to specify the prior distributions for mu and lambda. So here, mu is distributed as a beta distribution. So mu is a beta distribution, uninformative, but is censored so that the average success rate is above 50%, so 0.5 to 1. And then we use a gamma distribution here with what is considered uninformative priors for lambda. And then we do the reparameterization where we just calculate sigma, which is 1 over the square root of lambda. Lastly, then, we're just also going to do some posterior predictive checks. So predicted phi here is normal distribution of mu and lambda. So these values that we're going to estimate from interval 0 and 1. All right. And here we go then. So this code, it looks very similar where we just specified the number of people's successes, number of questions, initialize the parameters. We identify that there are additional parameters we want to monitor, this time mu and sigma, and now we just do our sampling. And here are the results. Let's print the samples, and we see the average success rate. We have the predicted phi. So notice how the predicted phi and the average phi are similar to one another. which is what we want, right? Yeah. And then we have small amount of variability surrounding this success rate that we estimated for each of the individuals who are considered knowledgeable. Additionally, then, we're going to get the thetas for each of the individuals across the entire sample. And in this case, the thetas are going to correspond to the thresholds for z here that we specified, where, for theta 1 through 5, it's going to be around 0.5 because they're in the lower group, And then for more interestingly is this value of the success rate we get for the other individuals, which now we can see varies a little bit here. So, we have someone who is really, really knowledgeable here, subject 13, who scored a 39. And then we have someone who's not so knowledgeable. So here, like 81. But overall, everyone is still above that success rate, which makes sense. And then in terms of just how well we were able to identify or predict whether someone was part of one group or another, it looks like we did a really great job. I'm pretty confident in these estimates, similar to the last question. So similar in that we were able to get more information about it, but it didn't really change our interpretation of the results here. Cool. Compare the results. Like I said, okay. So we didn't really get a difference in interpretation here. We're seeing the same sort of a pattern where those final or the first 5 subjects are not knowledgeable. The following are knowledgeable. Interpret the posterior distribution for predict phi. How does this distribution relate to posterior mu? Well, predict phi is the value of mu that we would predict given our posterior distribution. So if we wanted to go and try to guess what would be the success rate for someone who is knowledgeable, our prediction would be this, which corresponds nicely or closely to what we saw. And the actual value of the average for the success rate of phi. Yeah. In what sense could the latent assignment of people to groups in this case study be considered a form of model selection? In what sense could the latent assignment of people to groups Well, it tells us model selection, not model comparisons, right? I'm thinking of model comparisons right now. That's where my mind immediately goes when I read this question. And it makes me think, in terms of model selection, though, it makes me think that, we have 2 potential or viable models for test performance. We have a model for guessers and we have a model for people who studied. Let's see. I'd be interested to know. There are 2 rival explanations specified as statistical models for the data. These are guessing or knowledge-based responding accounts. When a participant is assigned to the guessing group, this means that that particular participant, we believe, is a guessing model, is a better explanation for the observed data than a knowledge-based model. Okay, so that's how model selection. And like I said, so we were able to identify these two models for knowledgeable and guessers, and Z then helps us choose which of these models is a better fit given what we observed in the pattern of the individual's responses. Oh, and just to be clear, phi is what we'd expect to be the success rates when we draw samples from a Gaussian distribution of mu and sigma. So if sigma was 0, there being no variability, then mu would be equal to sigma. But because we have a small amount of variability here, as shown by sigma, the predicted posterior distribution for phi is a little different, but not so much because there's not that much. Great. 6.3. And I think, let's see. Oh, we'll see. We might have more time. Alright, so we have 10 folks that go in the lecture, 20 questions. Whew. Binary, so this is if they got the answer correct or not, person, and then this is a given question, and this is one lecture. So we want to know two things. It's first, how well each person attended to the lecture, and that is reflected by the amount of questions that they got right. And then the second is how difficult each question was. So the probability of getting a given item correct varies because some are harder than others. However, the success rate across a given person also varies because some people pay more attention than others. And so let's take a look at the graphical model that represents that. Here we have the model where we have a distribution of i's for the people. We have a distribution of j's for the questions. The success rate, so these cells in this table 6.1, are representing a binary yes or correct or not correct for a given subject for a given question. So k sub ij. So those belong to both of the squares here. Right? So that's how that's supposed to be interpreted. And then we have these two rates. It looks like rates, betas. Let's see. So we want to infer p sub I for the people and q sub j for the questions, and then those combined are going to give us some assessment of the overall probability of success rate for a given person at a given question. Cool. Right? Ith probability. So this is listening. So we're interpreting this as listening to the lecture. Listening as reflected by the rate of success, I guess, for a person. And then this is difficulty of question, QJ. And then multiplying them together gives us the overall probability that a given person answered a given question correctly. So let's pull up the code. Oh, no. I know I just talked through this question, but I really want to use the stand code for exam 2. So I'm just going to go back to exam 2 just to at least we answered the questions, but let's just at least talk through the model code for stand 2. I think it would be really useful. Like I can't keep forgetting to do it. So from my understanding up to this point, stand code has 3 main things you have to specify, and then has additional things you can't specify. So the 3 main things you have to specify are data, parameters, and your model. And then we have these other things you can specify, like transformed parameters, transformed data, and generated quantities, right? So those are additional information that we want to incorporate, but the bare bones require that you have data, parameters, and a model. So in this case, the data are, this is from exam scores, right? So individual person has to have a lower bound of 1. So we need at least 1 person in our sample, and then a lower bound of 0 in terms of amount of successes a given person can have, and then a lower bound of 1 for the number of samples, so number of questions we have. Ooh, switching back and forth, sorry. And we want to transform the data, so we have real psi, so a discrete value for psi, where psi is just going to 0.5, and then parameters, we have this vector of phi, which is limited by these bounds, and then each person is going to get one, because this is the hierarchical model, if you recall. And now we have mu, which we need to specify because keep in mind that phi is going to be distributed from mu and lambda, right? So we specify the 0.5 to 1 because, as said before, we want to do this truncation or interval. And then we have lambda of 0. And then we have a pre-phi, which is also between 0 and 1. So pre-phi can be anything, and that's going to be reflective of how accurate our posterior predictive estimate is of mu, of the distribution of success rates for the knowledgeable group. Now we're going to transform some of these parameters. So it looks like vector 2, LP parts P. So we have a vector size 2 and LP parts P. I don't know what that means. Log probability. So we have a vector 2, log probability of each person. We have a real value for sigma. Second group, inverted square of lambda sigma. So that's just the distribution for prior for the second group. Standard deviation. Data follows binomial with a rate given by each person's assignment. So for a given person, person assigned to 1, it's going to be equal to log 0.5 plus binomial log success and phi. So we're using some binomial log distribution. And then LP parts 2, binomial log, we have log 5 plus binomial log success and psi, which is 0.5, right? So this is going to give us each person belongs to one of two latent groups with the rate given by each person's group assignment. So whether you have one of these two values is going to tell me if you are in one of these. We have this two vectors, right? Two vectors. P vector phi. And we have to then do the model. So lambda is prior distribution, and the posterior predictive, so pre is normal, and then truncated interval 0, 1. And then the second group from the sensor Gaussian distribution is phi, normal, mu, sigma, 0, 1. Posterior predictive, check. Distribution for each of the phis. And then incremental log prob, log sum, LP parts I. I don't understand this yet. And then, so do some incremental log probability of the sum of the parts. And now we want to generate Z for a person, and Z can be, or we want a vector 0, 1. We'll call it theta, so it's the success rate. And so for a given person, this we have a vector 2 called prob. Prob is going to be a softmax, and it's going to be made up of the parts for a given person. And Z is going to be a Bernoulli. The prob is 1, 0.5. And theta is going to be Z equal to 1, then it's going to be multiplied by psi. And if Z is equal to, or 0 is equal to 0, multiplied by psi. If Z equals to 1, multiplied by phi. And there you go. P is equal to P, K is equal to K, and just demonstrating these are what these are going to be equal to in correspondence to what we specified in the model. Same sort of stuff. Alright. The one thing I don't understand is incremental log prob still. So I'm just going to take a second to do that. Oh, and this is one of those deprecated statements. So underlying log density accumulator, but really we're just going to use target plus equals u now instead of that. So instead of this, it's going to be like target plus equals logsum. Looking on a log scale, multiplication is converted to addition. LP parts is just a vector P that has something in it that we specified. And this is just going to be the sum of the vector. This is summing the vector incrementally. Summing the vector for a given person. All right. Well, we worked through the code. So now I'm just going to take a second. We're going to move back. We're going to be switching gears back into 6.3, 20 questions. You know, it's important to just get some exposure to the stand code as moving forward. That was really helpful. So now 20 questions again, 10 people, 20 questions. We want to know who's paying attention. We want to know which questions are difficult. We have this model, graphical model. Let me open the code. And it looks like we'll be able to, maybe, we got 2 questions, 3 questions. We might be able to get through this. So let's open the 20 questions. 20 questions. Jag. And now I need the 20 questions. Text. It's only one text. So this model does not vary across jags and stand code or winbugs code. Taking a look at the model then. For a person, 1 number of people. For J is the number question. We have K, success rate for a given person of a given question, Bernoulli distribution theta of that. So we're going to have theta for each of the people for each of the questions. I think. So now we have probability correct as a product of question by person rates. Right, so for each person, for each question, let theta ij be described by the probability of attentiveness and the probability of difficulty for a given person for a given question. And then we set the priors for the people in the questions, which are distributed beta distributions, uninformative. So simple. Let's see what the code does. Nice. Runs. We get these. And then print symbols as well. Okay. When you use winbugs and you want to sample missing data, you cannot just return K to R as you can with MATLAB. Most likely the reason is that K is a matrix and say K13 is a single number. Winbugs will sample K13 when it contains NA. but R will not accept a sequence of samples K13. This means the following. 1. Using R to win bugs, you can tell win bugs to monitor and return K when you set debug true. You can inspect the results, but when you return to R, WinBugs is unable to pass on its results. One clumsy way around this problem is illustrated by 21 questions na.text. Note JAGS does not seem to have this problem, and you can just examine K. So basically what that told me is, good stuff. Let's go JAGS. No problems here. But we did monitor this NA array anyway. But it doesn't look like we got any values for the NA array. Here we initialized QP. We want to look at NP, NQ, and K. Or that's the data list we have. I'm working at the first data set, which is a complete data set. We create a matrix. Sort of looks like the table. Supposed to represent the table: 10 people, 20 questions, answers in the cells. And then this is just going to run this one because we don't have an NA. But it looks like we're going to be working with the NA for the next question. So here we're getting a probability of success for each of the 10 people. So attentiveness across the people. We have some folks not attentive whatsoever. We have other folks, like 5, who are very attentive, or number 1, extremely attentive. And we can take a look at the table to verify that. So here, person 1, really just out here, loves this professor. It's probably his PI. He's like, wow, so insightful. I'm so glad I came to lecture. And it doesn't matter how difficult this question is. I'm going to do my all. And it looks like no one's really getting this final question right, except maybe this guy who's probably guessing. But let's take a look at question 20 and see that question 20 was pretty difficult relative to other questions. Question 19, extremely difficult. No one got it right. So, boom. So we have this distribution of, we have these posterior distributions for each of the questions in terms of difficulty. And now we have posterior distributions for each of the people. And then I believe we should have, that's it. Alright, so we're deriving these rates. I'm curious, where'd data go? Do we not want data? It'd be cool to see theta. Draw some conclusions about how well various people listened and about the difficulties of various questions. Do the marginal posterior distributions you are basing your inference on seem intuitively reasonable? Yeah, they do. This graph might actually come in handy now for a second, finally. Let's just zoom it. Where we see the people who are the rock stars and people who are not. we see my favorite students and we see my not favorite students. I'm kidding. And then we see the challenging questions and the not so challenging questions. relative to performance of this sample of students. Right. Good. That makes sense. Now suppose that 3 of the answers were not recorded. For some reason, they just didn't fill them in. Our new data set with missing data now takes the form of 6.2. Oh no. Bayesian inference will automatically make predictions about data that's missing by using the same probabilities models generated from the observed data. Missing data are entered as none or NA. So NA in our case, including the variable k as one to monitor when sampling, will then provide posterior distribution for missing values. That is, it provides information about the relative likelihood of the missing value for each of the possible alternatives using the statistical model and the available data. So let's go check out if we got some reasonable inference here. And it looks like this is also implemented in a different script. So it uses a different text. So we have 20 NA here. So priors for people and questions. So we have an NA array, and we had to identify each of the given values that we are in our array. We identified which of the particular people and questions are missing. So we're just specifying that here. Looks like. And now we're going to set that data set to 2 and see what happens. Great, so we're going to get these values again for each of the folks. And we're going to get values for each of these. So this is K, the probability of K, posterior distribution for K. So that means that it's likely question 2 was incorrect. So, or NA array 2, so 8, 5. So the 8th person, 5th question, 8 persons, 5th question, it's likely it was incorrect. And why is that the case? Well, we're using data that from the difficulty of the question as well as the performance attentiveness of the person. We see this person didn't even get anything right. So if we go look at person 8 here, we have a very low attentive rate. And so it makes sense for us to infer that the question would have been wrong. For NA1, 113, say it's missing. This person, beforehand I was identified him as a rock star, right? So this is really going to come down to how difficult was this question. We know this person was attentive. This person was attentive here. The question 13 is an easy question. So given that the person's fairly attentive and the question was easy, we're predicting that they got it right. We're pretty confident in that. Lastly, for that last one, it's less likely that person got it right. But let's see, this person 10. So they're really up in the air, guessing sort of around 50. And for this particular question, this question is an easy question, but the person is not attentive. So we're not really sure, but it's less likely that they get it right, it looks like. And once again we get these intervals here. So question 1's probably right too. So this is the missing values, interpolated, missing values. Then we have the distribution for the subjects who are likely to be attentive, most likely to be attentive, and we have the questions that are the hardest. How does this change across observations? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not really. Looks like we still got the same 5 folks. And questions. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 1, 2. Yeah. So it didn't penetrate the data set, right? I mean, having a couple missing values here, and we were also able to fairly accurately interpolate them. Oh, and I mean, one other thing that I guess we didn't do here is just to look at what was the actual answers to each of these questions. Is it the same data set just with holes? Yeah, it looks like the same data set just with holes. So person 1, question 13. Oh, this is not numbered. It was a correct, and it got it correct. I guess the most interesting one would this be to see this was a 0, and it wasn't sure, but it was pressing towards not correct. So sort of, it was on it was making its way towards indicating that it's not correct. So I can't say that directionally, but I can say that the probability here is leaning towards being an incorrect answer rather than successful, because it's under 50%. Okay. The definition of accuracy for a person on a question in terms of the product is very simple to understand, but other models of the interaction between person's ability and questions are used in psychometric models. For example, Rash uses a rate which is represented here. So we use an exponential where we're subtracting the attentiveness, we're subtracting the difficulty from the attentiveness. We're looking at the difference between these two values exponentiated over 1 plus this. So we're normalizing it. So we're going to get a value between two rates. And it just wants us to run that. Yeah, so it just wants us to take a look. Can do. And then we got the text. I don't see Rash M. So with respect here, all we're doing is changing our definition of So let's go back to using dataset 1. And now all we need to do is change this. We get very different results here. I'm not sure the scale of these, but it looks like this time around, subjects P, let's see, 1, 5, and 7. Code noodles, 1, 5, and 7. Oh, 1, 5, 6. Okay. It's in a different scale. And then we also get these estimations of question difficulty. And with that, questions don't seem to be any more difficult than one another. I see. So it just wanted me to go ahead and change the graphical model to implement the rash. So it actually just wanted me to go in and do this, where it looks like the only difference between the scripts is theta ij, and instead we're implementing rash. So we're just going to calculate the exponential difference, the exponential of the difference between the scores over 1 plus the exponential of the difference of the scores, and replace that. And that's the only difference. Oh, we got pesky space here for some reason. Yep, so you see? Good. Nice. So 2-country quiz example tomorrow. So we got, and just to be clear, what was the latent mixture portion of this question? Well, there are these underlying rates of attentiveness and difficulty for items, and we were able to infer those from the data. From that, I think we could go and reason that we could potentially identify some sort of grouping for questions that are more difficult, so hard and easy questions. We could also identify attentive and non-attentive students potentially doing some sort of discrete indicator, as we did in the prior examples when we were looking at exam scores. And as shown, we could model that in tons of ways, but this is a pretty nice, simple example to illustrate also missing data imputation. So these examples are really fun, and I look forward to keep moving through this chapter tomorrow. We'll start with 6.4 tomorrow then. Thanks for coming around. I appreciate you listening. I'll see you tomorrow.